All right, let's continue. Last time we actually talked about parametric curves, i.e., we have this thing. So a point in the space is x, y, x, y. A point on the plane, we have x, y. Now from number t, we can actually try to determine x equals xt and y equals yt. So that from t, so we can, from this rule, this determines a point on the xy coordinate, okay? As this number t changes in a continuous manner, then we get a curve, okay? Then we get a curve. So we get a curve, x equals xt, y equals yt. So we get a curve. Now the example that we talked about last time is this example. X equals sine of t, y equals cosine of t. Y equals cosine of t. Then this actually is a unit circle. So this is the unit circle. The unit circle. Let me insert the unit circle. Okay, so we have a unit circle. Then this is the angle is, so this the central angle is, so this x-axis, this y-axis, y-axis. The central angle is t. Okay, so we have this point q. Q coordinate of this thing, you can solve the triangle. You can solve the triangle. So Q is x coordinate, you can solve it. So the angle is here, this is angle T. So Q is sine T, x is sine T, sorry, the other way around. X is cosine, y is sine. Cosine T, y is sine T. So this x is, this coordinate is, this is the cosine of t. Cosine t, y is sine t. Okay, so as this angle t changes, this q, the point q, will change out the unit circle. Okay, as t, the t is from 0 to 2 pi. As t changes from 0 to 2 pi, the endpoint q will change out of the unit circle. As t runs through 0 to 2 pi, the q, the endpoint q traces out the unit circle. Okay, unit circle. So we get a parametric equation of the unit circle. Okay. Another way of parametric, another way to write the unit circle is the following. Last time we mentioned another question, which is i.e. the rational point on the unit circle. Example. Rational points on the unit circle. Okay, i.e. find x and y in the rational field, in the field of a rational number, such that x squared plus y squared is 1. Okay. How do we do that? How do we work out this example? Okay, the idea is the following. we find a rational point on the circle. Then we do the find a point on the unit circle and then use the line intersect. Okay, so here we have the unit circle. Okay. All right, so we have a unit circle. Then, so this is x-axis. This is the y-axis. Y-axis. Okay. Now, this is y-axis. Okay. Now, first of all, we can find a trivial rational point. Trivial rational point. So this is -1, 0. Let this point be P. Okay. P is clearly a rational point. Now, by rational, it means a number R in rational. So a number X in rational number is equivalent to X is R over S. Here RS in Z integers, okay, rational number, and S is non-zero. Okay, so first of all, we clearly have a rational number. Then we use the intersection. Now, so if Q is a rational point, if Q x0, y0 is a rational point, a fraction, rational fraction, integers, okay, fraction of integers. Okay, then the slope. The observation is the slope T of TQ. T is y0 minus -1. The other is wrong. Minus 0. x0 minus -1, which is y0 over x0 plus 1, is rational. Okay, the rational numbers, you can do division. Okay, you divide to rational numbers, then again you get a rational numbers. Okay, addition, you can also multiplication, division, addition, subtraction. Again, it's closed. In this situation, we call the rational number is a field. Okay, so rational number, the number system is a field. Q is a field. Okay, now if you read it from German language, the word field means the corresponding word in German means body, means everything, body. Okay. Okay, because here Q is closed under division, multiplication, subtraction, etc. So this key, is a rational number. Conversely, if Q is a rational number, Q is a rational number. Then the intersection, then PQ, the line PQ intersects, then Q is also rational, a rational point. So this is equivalent to see this. Indeed, we check. Indeed, right? The line equation. Let L be the line equation. Y equal +1 to be key x. Be the equation. Be the equation of the line PQ, of PQ. Okay. Okay, from the line PQ we can write down, because we have a slope K, we have a point P. Okay, P is P, from the point P, we can write down the equation. Okay. Okay, then we find the equation. Okay, Q is the intersection PQ. Remember the 2 points PQ, P and Q. The 2 intersections of L and the unit circle. I.e., then the coordinate of P and Q should satisfy the equations. Okay. Okay, so we may find let Q the coordinate. So suppose Q is x0, y0. So we find x0, y0, the point Q, by solving the equations. The one equation is y plus 1 to be key x, and another equation x squared plus y squared is 1. We solve these 2 equations, and then substitute y into equation. Okay, substitute y. So from y we get y equal to kx minus 1. So substitute equation 3 into equation 2. Then what we get is x squared plus kx minus 1 squared is 1. Now if you rearrange this, the algebra x squared plus expand this k squared x squared minus 2 kx plus 1 equal to 1. So you get x squared plus k squared x squared minus 2kx is 0. 1 cancels 1. Now you factor out the x. So one solution is, the x0. When x0, then y sorry. The equation that I write is let's see. Okay, so the equation I write is not correct. So this will be this one. Yeah, in my notes I use a different point Q. So yeah. So here let's do it in this form. When x is -1, so this will be a +1 here. Sorry. So this we don't substitute the equation into 1 into 2. Sorry, because here you may use this point P. You can also use another point, which is you can also use this point 0, 1. Then this is the example that I use. Okay, in my notes. So let's do it again. So this will be totally different. Ooh. Oh yeah, actually this example. Oh, I see. Yeah. Okay. Yeah, I see the reason. Yeah, this point is Yeah, my choice is actually is better. Let's do it use this point. Sorry. Let's choose this point. Let's no longer use this P. It's unpleasant a little bit. Let's use this point Q. Q with the 0, 1, 0, 1. Yeah, in this case it will be better. Then the equation will be y will be, sorry. That's the reason I will explain in a moment. Y is kx plus 1. Yeah, y is kx plus 1. And it will be, this will be kx plus 1. Kx plus 1 squared. Okay, plus. Okay. In this case, it's easier to cancel this 1. If you expand it, you see 1 squared cancel 1, so that you don't need to solve quadratic. So this is the reason that we try to avoid the quadratic. Okay, so you see this case, another root is x times 1 plus k squared plus 2k is 0. K is fixed. So here x, you solve for x. Sorry. Is negative 2k. Then x is negative 2k over 1 plus k squared. So this is q. This point is q. This point is p. Q is our fixed. Q is our fixed 0, 1. P is x 0, y 0. Okay. So you see x0 can be right in this form. Then y0, you solve y0. Y0 is on the line. So y0 is kx 0 plus 1. You plug in kx x0. So you get this is negative 2k over 1 plus k squared times k plus 1. So you get this is negative 2k squared 1 plus k squared plus 1 plus k squared over 1 plus k squared. Okay, so finally this will be 1 plus k squared, y minus k squared. If you so the solution you can finally write in this form. Okay, so this x x0 you can write as negative 2k 1 plus k squared. Y is 1 minus k squared, y plus k squared. Okay, so here if you replace k by negative k, you can also forget it's negative 1. Okay, you see x, so k is rational number. So this implies x0, y0. They are rational numbers too. Okay, they are rational numbers too. Okay, so somehow we forget this negative 1. We forget this negative 1. You just replace k by negative k. Just a little substitution. It's very easy. So if you write this general solution as is, the rational number solution on the unit circle, then you can write it in this form. Okay, so k is rational. Okay. This contains every solution except one solution. This has this including every rational integers, rational numbers, rational solutions on the unit circle, except 1 point. Except when y is negative 1, x is x is 0. We only have except this point. We don't have 0, negative 1. Okay. So we get a rational solution on the unit circle. Now let's we solve this problem. Now let's change this a little bit. Now if we write k is rational, write k as m over n, So it's a right m n integers. Then we have x is twice m over n over 1 plus m squared over n squared, which is if you do multiply by n squared. Y is y minus k squared. Then you get m squared n squared over 1 plus m squared n squared. So this will be n squared minus m squared over n squared plus m squared. Okay. Now, if you write in this form, then finally you see x squared plus y squared, x squared plus y squared equals 1. Then you get 2mn, m squared n squared x squared plus y squared now if you write in this form, multiply both sides by the denominator, clear denominator. Then you get 2mn squared plus n squared minus m squared is n squared. Okay, you see, this is a squared plus b squared equal to c squared. This actually gives us mn, that is integers. So this gives us a universal solution for the Pythagorean triples. So ABC is a Pythagorean triple. Okay, so that we can get all primitive Pythagorean triples in this case. We can get all primitive Pythagorean triples in this manner. Okay, actually all Pythagorean triples you can write in this universal way. Okay, so here you can write as usually we write as n squared minus m squared. So here we abuse notation a little bit. B is 2mn. C is n squared plus m squared. Usually we write a first, n squared plus m squared. So abuse of notation, abuse other notation here. So AB is the switch. Okay. So this gives us all Pythagorean triples. Okay, all Pythagorean triples. For instance, if we take example. If we take n to be 2, m to be 1, then we get A is 2 squared minus 1 squared, which is a 4 minus 1, which is 3. B is 2 times m is 1, n is 2, which is 4. C is n squared, 2 squared plus 1 squared is 5. Then we get a Pythagorean triple 3, 4, 5. Okay, 3, 4, 5. Now, if we take n to be example, take n to be, see, that's 3, m is 1. Let's in this case we don't get anything new. Then you get n squared. A is n squared, 3 squared minus 1 squared, which is 9 minus 1. We get 8. B is 2mn, which we get 2 times 1 times 3. So we get 6. C is n squared plus m squared. So we get 3 squared plus 1 squared. We get 9 plus 1, which is 10. This we get, this is essentially 3, 4, 5. It's just a multiple of 3, 4, 5. You see, 8, 6, 10 is the multiple of 4, 3, 5. So again, we get a 3, 4, 5 triple. Now, n equal to 3, m equal to 2. Then we get A is 3 squared minus 2 squared, which is 5. 9 minus 4 is 5. B is 2 times mn, which is 2 times 3 times 2. We get 12. Okay, C is n squared plus m squared, 3 squared plus 2 squared. It's 9 plus 4, we get 13. So we get the Pythagorean triple, 5, 12, 13. Okay, 5, 12, 13. You can try to get any other cases. For instance, let's see. We have this Pythagorean triple. Anyone remember any Pythagorean triple? For instance, we can have this 8, 17. 8 is 17. So yeah, then you have another one. You can try to get this one. Yeah. Also, this is 17 here. This is 17. So c squared is 17. So 17 is n squared plus m squared. 17. So if you take a 4 1, if you take a 4 1, then you get 4 1. You see n to be 4 1, n to be 4, m to be 1. So you get a c squared is 17. Then you have 2mn is 2 times 1 times 4, then you get 8. Okay. Then you have n squared minus n squared minus m squared. This will be 4 squared minus 1 squared, which will be 15. Okay. So you have another thing, 5, 15, 17. It's also Pythagorean triple. Okay. So we got a universal way of Pythagorean triple. Pythagorean triple. Okay, this question, rational points on the unit circle. You see this is equivalent. You solve the Pythagorean triple, primitive Pythagorean triple, all the rational point on the unit circle. This is essentially the same problem. Okay, although they look different, but by algebra they are equivalent problem. This solution, okay, the universal solution. These solutions are known to the ancient Babylonian people. Okay, Babylonian people. If you know some history, the Babylonian people is around lived around in the Middle East, around in the area of Iraq, Iran and Iraq today. Okay, so these are known. This was known to the ancient Babylonian people. Some history. So it's around 17th century BC. 17th century BC. Okay, a good book, a good reference of this is a book written by a number theory. Reference book. So see, for some history, you can see this book. Number theory, this book, number theory. An approach. Through history, from history. From Hammurabi to Lysander. It's a really nice book to read. See page 9. So the author is Andrew V. It's easy to confuse this number series with Andrew Wiles. Don't confuse the Andrew Wiles. Andrew Wiles is the person that solved the Fermat-Last theorem. This Andrew V is also another big mathematician. Okay. So we solved this case, Pythagorean triple. Now, if we change a little bit, Um, okay. Now you may okay. We solved the problem of rational point on the unit circle. Now you may ask, what happens for other geometric other curves? Okay, other curves. For instance, we can write down many other curves. How do you find a solution? How do you find a solution? Okay, right now it's easier to solve degree 2 solutions by lower degree. Now higher degree is more complicated, we may expect. For this example. Now degree 2 curve, they are special. They are special. They are special. Now this is an ellipse. An ellipse. So find the rational point on the ellipse. Find the rational point. So find all rational point. On the above the ellipse. Okay, we can use the same idea. We can use the same idea. Okay, i.e., pick a rational point. Pick a rational point. Then intersect it with the line with rational slope. Okay, rational slope. Okay, so the idea is the following. So we have this thing. Sorry, it's y side. The y should be square root. This is the other manner. So let me either I don't want to plot it behind. Okay. Oh, why does it looks like this? Do we have better? Okay, this one looks nicer. Okay. So it's another way around. It's should be this manner. Okay. Oh, it's a y coordinate is square root. Sorry, this is right. The y square root is this manner. Okay. So it looks like this. This x-axis, this is the y-axis. Now this point is y. Okay, y. You can check that this point is square root 2. Square root 2. This is negative square root 2. This is negative y. Okay, so we can use this point. Use this point P. Rational point P. So P is y0. So you can write a line that is through P. Okay, through P. Either line. Okay. This point is Q. Okay, so line PQ. Suppose its slope is K, so you can write down y is K times x minus y. Okay. So you can find its solution. Write down its equation. When x is 1, y is 0, slope is K. So K is rational. K is a rational number. Okay. Then the intersection Q should be a rational point. Okay. Q should be a rational point. The idea is if you have a rational point Q on the curve, then PQ is rational. Okay. Now Q, you need to determine K. K you need to determine by Q. Okay. So you see, if K is rational, then Q is. If Q is rational, then K is of course slope is rational. Conversely, K is rational, then Q is rational, because they uniquely determine each other. Okay. Then substitute to the equation of this conic, this ellipse. So substitute y into the ellipse, the equation of the ellipse. Then we get x squared plus y squared. We substitute, remember, y squared over 2 is 1. We substitute y. So it's x squared plus t squared x minus y squared over 2 is 1. Okay. Okay, so what else? What do we do? So we solve, you see, now if you solve this quadratic, it's unpleasant. If you solve this quadratic, it's unpleasant. So we try to use another method. We try to factor this. Move this 1 to the other side. So this is x minus y, x plus y. So this k squared x minus y squared. So we know it has a root x minus y, so you can factor it. Okay, so you can factor it. So it's x minus y times x plus y half k squared x minus y is 0. So we have one solution. So x minus y is 0, so we get the point P. No surprise. Then the other solution, this is 0. Then we get a Q. Okay, so x is 1. So this is a P. This point P. Now this one you solve it. You get so you get 1 plus k squared over 2 x, which is, you get the right side, you get minus 1. So what do you get? X is 1 half k squared 1 half k squared minus 1 over 1 half k squared plus 1. So you get, this is k squared minus 2 k squared plus 2. This is of course in rational number because k is rational. Okay, k is rational. K is a rational number. Okay, so then you can solve y. So y is k times x minus y. You got a k. X is k squared then what you get is common denominator, k squared plus 2, k squared minus 2 minus k squared plus 2 multiply k. And then you take off the parentheses. You got a k squared minus 2 minus k squared minus 2. K squared plus 2. Don't forget this k here. So you get a k squared cancel k squared. So you get a negative 4. So you get negative 4k over k squared plus 2. So you get the parametric equation. You get this parametric equation. So we get x is k squared minus 2, k squared plus 2. Y is negative 4k, k squared plus 2. Okay. Okay. Now you see here the xy can be write as a rational function of k. Okay. So we find parametric equation, parametrization of the curve by rational functions. Okay, this turns out to be a special property. Now, if I write down a general curve, for instance, this curve, you can easily write it as, a parametric equation. Find this parametrization in rational functions. Now, this is special property. Not every curve you can do in this manner. Not every curve you can do it in this manner. Okay. For instance, example. This y squared equals x cubed minus x. This is degree 3. Okay, degree 3. Now this one, you cannot find. Try the above idea. Try the above idea, and see how it feels. Try the above idea, and see how it feels. For this one, we cannot solve a rational parameterization of the curve by rational functions. Okay, because here you solve degree 3. Degree 3, that will cause trouble. Okay, then in this example, first of all, you can find a rational point. For instance, x is 1, y is 0. You can find a point. You can use the same idea. Let's see what happens. Okay, then the intersection in general, you get 2 points. And then somehow you need to solve a quadratic, and it's not so lucky. The quadratic can find you get a perfect square. Okay, when you take a square root. Okay, when you solve quadratic, the discriminant is not in general a perfect square. Okay, so you need to be really lucky to find which case actually you get a perfect square. Okay, so this kind of thing is called elliptic curve. Elliptic curve. Okay, elliptic curve. Okay, so in general for elliptic curves, we don't have a rational. It's not a rational curve. Okay, you cannot find a rational parametric equation by rational functions. Okay, so this thing does not exist for this curve. Okay. Okay. More example. Maybe I'm missing another example. Okay, try the above idea. For the curve. X squared minus 2y squared is 1. Okay, so you can use the same idea. Okay, you can use the same idea to get a rational equation. Okay, to get a solution. Okay. Rational points on curves. This is a huge topic. So let me mention a little bit, give some remark of this topic. So this is a huge topic. Rational points on curves, algebraic curves. Huge topic. This is also called arithmetic geometry. So the curve is geometric thing. And then rational points, these kind of points, numbers are not algebra. So in some sense, there's another name is also called algebraic geometry or arithmetic geometry. Also called arithmetic geometry. They are the same thing. Different name, arithmetic geometry or algebraic geometry. This is a really important topic. Of course, this is a huge topic. We can only give a really easy remark. Now, arithmetic geometry or algebraic geometry, This is really important. And right now, for instance, what are known? What is I know? What are unknown? What are I know? Okay. For instance, rest point on quadratics. This is totally solved. Totally solved. Degree 2 case. Degree 2 curve. Totally solved. Totally solved. Now degree 3 case. Degree 3 case. Okay, degree 3. Degree 3 curves. Or you know, for instance, another name is called elliptic curves. Elliptic curves. These are many open problems are solved. Okay, partially known. Okay, partially resolved. Not totally solved. Partially known. How to find the its thing. But there are many open problems. Many open problems remaining. Many open problems. Open problems. Open problems. So you see, from the solution of the unit circle, you know, many years ago, 18th century BC, up to now, you know, human beings solved only very limited case. Now we only know how to do degree 2. Degree 3, maybe that's the partial result. Okay, even today, you know, so it's degree 3. There are many open problems to be solved. Okay, so this is also the task for the 21st century mathematicians to solve this kind of open problems. Okay. Now for the elliptic curves, you may heard the story from Andrew Wiles, how he solved the Fermat theorem. Is actually use this degree 3 curve, elliptic curves. Okay. And also there's a $1 million problem. $1 million problem. $1 million problem offered by the Clay Math Institute called BSD conjecture. BSD conjecture is actually related with elliptic curve. Okay, BSD conjecture is related with elliptic curve. Okay, so it's $1 million problem. Okay. Now this BSD is a letter for mathematicians. Okay, BSD. Now it's really funny story. Okay, for people who don't know this, you see BSD conjecture, people may think, well, this is three people, but it turns out to be this is actually two people. B is one people, SD is another people. So somehow you will be really surprised to see 2/3 of people. Okay, be careful. Another application of this reference points on elliptic curve is cryptography or information security. Right now, what we do for information security, the algorithm, this is actually we use elliptic curves. Okay, so this is actually we use this kind of algorithm in elliptic curves to do cryptography. What's the idea? The idea is the following. Now, if I give you a solution, of this reference point on the curve, well, you just plug it in and check. It's very easy. Okay, it's very easy. Now, if I ask you how to find a huge number of solutions, this turns out to be hard. Okay. Now, this kind of cryptography is actually essentially you need to use one direction is very easy, like when you use your key to unlock your door, open the lock. Okay, it's easy. Now, another way is difficult. Without the key, if you don't know what the key looks like, if you try to construct a key, it's difficult. It's difficult because you don't know the shape of the key. There are too many configurations of the key. Okay, there are too many choice. It takes a lot of time to a lot of choice to make the right choice. This actually has really important applications in industry, and also this is actually a beautiful subject. Okay, a beautiful subject with in mathematics, and this somehow is related with what we talked about last time, elliptic integrals. Okay, elliptic integrals and elliptic curves, somehow these kind of things are related. They are beautiful area in the mathematics. Okay. Another thing that I want to mention is another special curve. Historyically interesting. This is called the cycloid. The cycloid. Okay. The cycloid. Interesting and important. What is a cycloid? What's a cycloid? A cycloid is a curve obtained in this manner. Obtained in this manner. A cycloid is, suppose, let me insert a circle. Okay, suppose we have a circle. Now, a circle, we put this circle, so suppose this circle travel on the horizontal line, so it looks like a tire. Okay, so this is the flat, this is the ground, Okay, this is the ground. Now, on the tire, you have a point, you have a marked point, P. Mark the point of the P. Now, as the tire travel along the surface, okay, rotation, then the end point P, the marked point P, trace out a curve, okay. The circle center is C. Okay, so the point P trace out a curve as the circle travel along the ground. So as the circle C travels on the ground. Okay, then the point traced out a curve, and this curve is called the cycloid. Okay, the curve is called the cycloid. Which is called the cycloid. Okay, the cycloid. Okay. Now, how do we write down the solution of? How do we write down the equation of this cycloid? Parametric equation. Okay. Now let's do some observation. How do we write down this the coordinate of P? Okay. How do we write down the coordinate of P? So first of all, we put into coordinate. So this is x coordinate. This is y coordinate. We put y coordinate here. Okay. Suppose we start from 0, 0. Okay. Suppose when maybe we make a little further. So the point P, the initial point P is here is rotate. Somewhere is here. So P start from here. Then it looks like this. The curve does the what as use your imagination, geometric imagination. So what does this look like? Okay, so somehow it looks like this. Okay, symmetric. It's symmetric. Use your imagination. Okay, use your imagination. Okay, how do we find the point at P? How do we find the coordinate of P? Now we use some information, new information. Suppose the radius of this thing is R. The radius is R. The tangent point is T. This is O. This is O. Now this point P is XY. So P is XY. X or Y. XY. This point is Y. I need to write here. This is X. This is Y. Okay. So we have now how do we find XY in terms of a known property? So the radius is R, and this is theta. We don't expect that we can. Okay, too easy solution. Okay, so from the geometry of solving this geometry figure, so you see the y coordinate is we can solve geometry. We can use y coordinate of this thing is the radius r subject the angle theta. Okay, the theta is the central angle. So we can solve y, which is the radius subject apart. Okay, so this is actually y. This is y. Okay, so we can subject. So this is the hypotenuse is R. So this is the C, the point C. Okay, let this point be Q. Solving the triangle CPQ. From the triangle CPQ, right triangle CPQ. Okay, so CQ, what is CQ? In right triangle CPQ, CQ is hypotenuse CP times, so you solve a triangle, so you get it. This is CP times cosine, cosine theta, yes, cosine theta, okay, cosine theta. CP is the radius, this is R cosine theta, Now, so then Y is R minus CQ, Now, if Y goes beyond, beyond the radius, so then CQ will be negative. So this will be R subject R cosine theta. Okay. So Y will be if you factor out R, so this R is constant R Y minus cosine theta. How do you find X? Okay, X. First of all, OT is how far this circle traveled. The tangent point traveled is actually exactly the arc length. Okay, equal to the arc length of PQ. Okay, OT, the straight line is exactly equal to the arc length of the arc PQ. Okay, equal to the arc of the PQ. Arc of the PQ is very easy. Okay, arc of the thing you can find easily. Okay, you can find it very easily. So this will be R times theta. Okay, now we find OT. Now we need to find OX. Now we need to find XT. XT is what? XT is, to find XT, you see, to find XT, in triangle CPQ. So this equal to XD equal to PQ. Equal to PQ. Equal to PQ. Now equal to PQ. PQ we can solve triangle. In triangle, in right triangle, this in right triangle CPQ. Okay, solve PQ. Solve PQ. Okay, solve PQ. CPQ. Okay, CPQ. Then you solve PQ. This is, you know the hypotenuse, you know the opposite angle. Okay, so this you can easily solve by solving triangle. So this is r times sin theta. R times sin theta. And then you can, from this geometric figure, then you can solve. Then what you can solve is okay. So you solve OX, which is OT subject XT. So OX, okay, OX is OT subject XT. So this will be OT will be R theta, XT will be R sin theta, you subject. So this will be R times theta minus sin theta factored out. Okay. So this parametric equation of the cycloid, so theta is in real number. Okay, then you get a parametric equation of the cycloid. So parametric equation of the cycloid is x is, we choose initial point to be 0, 0. Okay, x is r, we just did it. Okay, about sin theta minus theta, theta minus sin theta. Y is r, y minus cosine theta. Y is always positive. Okay, theta is in all real numbers. Now, first of all, we may see this pattern repeated, because by symmetry, after repeat this circle one round, we will recover the initial position up to, you translate this thing up to the distance. So this you should expect this thing to be periodic. So like a sin x, okay, like sin x is periodic, it's curve. Okay. What's the period? The period is clearly 2 pi. That's clearly 2 pi r. Well, it's periodic. The period is, the period is 2 pi r. Well, period is 2 pi r. Y as a function of x is periodic. Okay, for this example, you see, it's hard to find explicit expression of y in terms of x. Okay, it's difficult to find explicit thing of y in terms of x. Okay, let me give a remark of this cycloid. The cycloid is, in some sense, important. Physically. So another question of this cycloid is the fast descent curves. Curve of fastest descent. Okay, this question is posted by Johann Bernoulli. Okay, so for this example, ask this. Suppose we have 2 points A and B. Now, what is a curve? What is a curve that is such that if you have a ball, put at A, and when it travel to B, here this AB, the curve AB is smooth, so there's no friction. Now from mechanics, then determine the total time, the shortest time from A to B. If you put a ball at A from A to B, So this is called the curve of fastest descent. Okay, this is posted by Johann Bernoulli. Okay, Johann Bernoulli. Johann Bernoulli. You may heard that the Bernoulli family is, is famous family in Europe. That is famous for mathematicians. There are several mathematicians with last name, family name Bernoulli. Johann Bernoulli. This is posted in this term. So posted asked by Johann Bernoulli in publicly in this 1696 in this journal. In the journal. Let me write down the journal name. So if you can read Latin, so in Latin this means so this means the acts of knowledge or something. Okay, in Latin, this Latin name for acts of the knowledge people. Acts of the knowledge people. The journal's name. Okay. Some history of this thing. Johann Bernoulli, he has a younger brother called Jacopo Bernoulli. So question? Okay. Jacopo Bernoulli. So this is the younger brother of Johann Bernoulli. Also, they have an uncle. Okay, this Bernoulli brothers also have an uncle, also a mathematician. Jacopo Bernoulli. And somehow it takes around 2 weeks for Johann Bernoulli is a top mathematician at that time at Europe. It takes him 2 weeks actually to solve this. It is said that it takes two weeks for Johann Bernoulli to solve this problem. And then Johann Bernoulli, once he finds a solution, then he tried to challenge the top mathematicians. At that time, the people has the highest reputation is of course Isaac Newton. Isaac Newton at that time he already past his prime ages, so he's over 50 right now. So it's in some sense a little old. And Johann Bernoulli sent a letter to Isaac Newton. And Isaac Newton, you may guess how long it takes for Isaac Newton to solve this problem, the challenge. Actually, it takes Newton just 1 night. So you can see how the talent of Isaac Newton, how good Newton is. Okay, Isaac Newton. So there are several people from Europe doing this kind of problem, trying to take this challenge. Okay, so Isaac Newton is not super interested in this mathematical problem. He's more interested in physics thing. And once Newton received the letter from Johann Bernoulli, he started working on this. It takes Newton 1 night. Okay, takes 1 night. Just in 1 night, solved this problem. In 1 night. So you can see from the time it takes Newton 1 night, it takes Johann Bernoulli 2 weeks. And then how long it takes for other mathematicians, I'm not totally sure. And Newton is very humble. He find a solution, and he sent this solution to the journal, or replied to the journal without signing his name. Okay. Now Newton at that time, he already published his famous book, the principle, the famous book, and he has his own way of writing. He has his own style of writing. And Johann Bernoulli once received Newton's letter. Johann Bernoulli once read Newton's letter, and he immediately realized where this letter is coming from. Okay. So that's a setting set of Johann Bernoulli. Okay. So he realized immediately. What he said is, he realized the line. Okay, the line by looking at the trace of his poem. Okay. So he realized this immediately to Isaac Newton. And some other mathematicians also solved this. Leibniz, Newton, Leibniz, they are enemies. Okay, Leibniz from Germany, and also his brother, Jacob Bernoulli. Also find a solution. Somehow the Bernoulli brothers has a little argument about the discovery of this solution. Somehow there's some a little dispute between these Bernoulli brothers. And also L'Hopital. Remember this mathematician L'Hopital? L'Hopital. He's from France. L'Hopital is one of Bernoulli's students. Okay, L'Hopital is one of Bernoulli's students. I don't know which Bernoulli teach. You can search. I forgot which Bernoulli taught L'Hopital. One of the Bernoulli actually served as a private tutor of L'Hopital. And it's amazingly that this proof of L'Hopital was published at 1988, several centuries after this thing.